is dealing with special quadrilaterals in these kinds of situations. It's going to want you to, in 6.6, when I say it, I mean the Moodle questions, and the test questions related to this are going to ask you to do essentially two things. Identify special quadrilaterals based on some limited information. So given some information about this mystery quadrilateral, what is it? What could it be? Or prove that a quadrilateral is a special type of quadrilateral, such as a trapezoid or a rhombus, etc. Now, let's just list them off. We're not going to get specific yet, but what are the different kinds of special quadrilaterals that we've talked about? Let's just rattle them off. What's one? Not Square. There's one. Rectangle. There's another one. Rhombus. Boom. What's another one?
Diamond.
Meaning a kite.
Yeah.
Okay. Or a rhombus, probably.
Yeah.
Diamond would be maybe like a rhombus. A kite. Okay, kite would work. What else? A couple we're missing. A couple words we haven't said that we can talk. We have talked about. Parallelogram. Could be named all the special ones, but a plain old parallelogram. And then what's the other one? No. Trapezoid. And then what's the one special trapezoid we dealt with? Isosceles trapezoid. Good. So there's a bunch of them. Now, our goal is to be able to recognize, what are the special characteristics of each of those kinds of quadrilaterals we've talked about. Okay. So, in general, well, first let's just talk about this. This you got to know. This is one that this slide right here, and I've got the PowerPoint already on the website. You got to understand what this means. This is a hierarchy. It's like a flow chart. If we start at the top, we're coming in with the most general place we could be, which is just any quadrilateral. Okay. Now, if we're going to move up from just a random quadrilateral to something more unique and special than that, we've got to say something about that quadrilateral. So if we're driving down the road and we're coming to a three-way fork in the road here, and we want to travel from the quadrilateral freeway to the kite street, what has to be true? What are the characteristics of a kite? What do we know about a quadrilateral? If a quadrilateral is going to be a kite, what must be true about that quadrilateral? Two pairs of congruent sides. Okay. Now, are there any opposite parallel sides in a kite? No, there are no pairs of opposite parallel sides. Are there any pairs of opposite congruent sides?
In a kite?
In a kite?
No.
No, if we look at our general, run-of-the-mill kite, it's not so great, but you get the idea. These sides are congruent, and those sides are congruent, right? So we get two pairs of consecutive congruent sides. But opposite sides are never parallel and never congruent. See, so those are the characteristics of a kite. If it fits the bill, that stuff is true, then it's a kite. Okay? That's one avenue we could take. Now, what about if we turn on to parallelogram drive? What's going on there? Yeah, right down the road. Remember, the road is splitting here. It's forking. So if we turn on to parallelogram drive, what are the characteristics of the quadrilateral then? Okay, now here's something interesting happens. What's the definition of a parallelogram? Well, no. The definition of a parallelogram is what?
Parallel.
What's parallel? Say it again. Yeah, two pairs of opposite parallel sides, right? That's the definition of a parallelogram, a quadrilateral with two pairs of opposite parallel sides. So one way that we can limit our quadrilateral to be a parallelogram is by fitting that definition. Now, we studied parallelograms in detail, and we found out that there were some characteristics of parallelograms, some properties that didn't rely on the definition. What I mean by that is we had 4 theorems that said if parallelogram, then stuff. Like if parallelogram, then opposite sides are congruent. There's one property of a parallelogram, right? So if we've got a quadrilateral with two pairs of opposite congruent sides, that's a parallelogram, guaranteed. If parallelogram, then opposite angles are congruent. So if we've got a quadrilateral with two pairs of opposite congruent angles, hey, that's a parallelogram. We don't need to know even that or demonstrate that the sides are all parallel. Maybe that's not easy to do, but we can see right away that the opposite angles are congruent. So when we're trying to show that a quadrilateral is a parallelogram, we can either use the definition, two pairs of opposite parallel sides, or we can use any of the properties that go with that shape, right? And we had a bunch of them. In addition to the ones we already said, we said if parallelogram, then consecutive angles are what? If I take any two consecutive angles in a parallelogram, supplementary. Yeah, their measures add to 180. If parallelogram, then what about the diagonals? The diagonals are, what do they do? Congruent. What do they do? Bisect each other. Sure. Okay. Now, even that one freebie, we said that if we've got a shape, we have two pairs of sides, or one pair of sides, sorry. One pair of opposite sides that are both parallel and congruent. We got a little sneaky one there. Says, well, then even that has to be a parallelogram. So we get all those ways of showing it's a parallelogram. Now, once we're on parallelogram drive, how would we turn on to rhombus way? We're running out of words here. Streets. How would we turn on to rhombus way? We know we've got a parallelogram. What's true of to make it a rhombus? What has to be true?
Go up.
Maybe. But what has to be true?
Hold on.
Maybe. No, they're off limits for this drive. We don't get service here. So what's true of a rhombus? What's a rhombus? Say it again. More than that. More than that. What's true of all the sides in a rhombus? They're all congruent. That's the definition of a rhombus. They're all congruent, right? So if we knew that was the case, we've got ourselves a rhombus by definition. There are some properties of a rhombus we could rely on. Okay, if we knew we had a parallelogram, say we already knew that much, there are some things that are only true of a rhombus for a parallelogram. They have to do with the diagonals, right? What if the diagonals met at, or were perpendicular? Well, there's only one kind of parallelogram with perpendicular sides. What is that? It's a rhombus, right? In a rhombus, the diagonals always meet at a right angle. There's another kind of weird one we don't use very much. Well, okay, but a square is a rhombus, isn't it?
Yeah,
right. And a rectangle, right. So if the diagonals bisect the opposite angles, cut them in half, then that's also a rhombus. That's a characteristic of a rhombus. Okay, so if those things are going on, then we know we've got a rhombus. Rectangle, someone already said, with a rectangle, well, actually we didn't say. The diagonals in a rectangle are what? There's a lot of stuff going on here. Yes? Yeah. Okay, what about the diagonals in a rectangle? I know I'm kind of putting you on the spot. There's a lot of just the nitty-gritty, but see, test yourself, you know? What's true of the diagonals in a rectangle? You're going to have to know all this for the test. Well, they must do that because a rectangle is a parallelogram, so we get that for free. But what's special about just the rectangle? Not only do they bisect each other, they're congruent. Very good. If the parallelogram has congruent diagonals, it's a rectangle. Or if it just meets the definition. What's the definition of a quadrilateral that's a rectangle? It's a rectangle. Well, okay, that's, yeah, be true. But what's unique? I mean, a rectangle is a parallelogram with what? What about the angles in a rectangle? Yeah, they're all 90 degrees. They're all right angles, right? So any parallelogram with 4 90-degree angles is a rectangle. And then if it's both at the same time, it's a square. So you get the idea, right? In order for us to start with a quadrilateral and say end up at a rhombus, we've got to go through a very specific bunch of conditions, right? Now, what about a trapezoid? If from the quadrilateral freeway, if we didn't have a kite and we didn't have a parallelogram, There's one other kind of special quadrilateral we could have, a trapezoid. Well, what's the definition of a trapezoid? No. Now a kite had, well, I'll let you, what about a trapezoid? What's the definition of a trapezoid? Quadrilateral what? Yes, sir. Ah, okay. Exactly one pair of opposite parallel sides. Not two. Can't have two, but just one. Right? So if we've got exactly one pair of opposite parallel sides, we got a trapezoid. And then we could have an isosceles trapezoid. We'll get into that stuff later. But you get the idea. You get the idea. This is how we could divide up and categorize a random quadrilateral. Okay? All right. So let's move on here. What about this one? Let's identify this. Quadrilateral ABCD has at least one pair of opposite sides congruent. Okay? What kinds of quadrilaterals meet this condition? Now, at least, what is at least one pair of opposite sides? That word at least one, that's important. Okay, there could be one, or there could be more, sure. Right? So in a quadrilateral, we've only got two pairs of opposite sides. So either it's one or two, but not zero. Right? So could it be a kite? Good. Does a kite have any opposite congruent sides? No, it doesn't. So it can't be a kite. This one has at least one. Okay, what else could it be then? It could be a trapezoid. Now, what kind of trapezoid would have one pair of opposite congruent sides? Isosceles. Could be an isosceles trapezoid. Right? That's a possibility. Right there, because it has a pair of opposite congruent sides. One pair. Right? What else could it be? Could be a square or a rectangle or a rhombus. In fact, it could be any parallelogram, couldn't it? Right? So, could be any parallelogram, including, I hid these for myself, rhombus, rectangle, or square. Any of those would work, because they all have at least one pair of opposite congruent sides. Could be a bunch of stuff. Okay, let's look at something here now, something a little different. This is interesting. Connecting midpoints of sides. When you join the midpoints of the sides of any quadrilateral, it does not have to be anything fancy. It doesn't have to be a special quadrilateral. Something happens. Now let's look at this in just a little more detail. So let's take. Oh, that's not what I wanted. Never mind. Okay, so here's my random quadrilateral. Nothing special about that one, right? If I cut that thing in half, I can always make a quadrilateral into two joined triangles, right? So you got to really follow this closely. This is pretty cool. If you can follow all this logic, there's something amazing that comes out of this that you would not have expected. Okay, so what if we join, let's see, let's join these 2 points with a diagonal. Okay, and let's take the mid-segment, or the midpoint, sorry, of both of these, of all the sides of the quadrilateral. Okay. Now we learned something way back when. A property of triangles. If I just focus on this triangle up here, if I join the mid-segments, or the midpoints, and create the mid-segment, you remember what had to be true of that mid-segment and the third side of the triangle? They're parallel. Yeah, they were parallel. And that's pretty easy to convince yourself that that has to be true, doesn't it? Because if we're traveling from this endpoint to that endpoint, well, I'm going to change the vertical position of the ant or whatever's walking from there to there. I'm going to go half the distance to the top of that triangle, aren't I? Same thing from here. If I start down at this vertex and walk up to that one, I'm going halfway to the top of the, think of it like a pyramid. Yeah.
Way to take up class time.
Okay, so sorry about that. So here we go. So those are parallel, right? Now what if I look at this bottom triangle or the left triangle, however you want to think of it? Same deal, right? I know that this mid segment is parallel to the third side also. So doesn't that mean that those two sides are parallel then? Right? Those two segments are parallel? Aha. Okay. Let me get rid of this one for a second here. Okay, now let's slice this quadrilateral the other way. This time let's cut it across there. Right? If I connect those midpoints again, create mid-segments, but this time, in the other triangles, what ends up having to be true of those two? They have to be parallel also, don't they? Because this is true. That mid-segment is parallel to the third side of the triangle, as is that mid-segment, right? So look what we've just created now. If I get rid of that diagonal and just leave the segments connecting the midpoints, look what I'm left with. I think this is just kind of amazing that this works the way it does.
With the ring.
Yeah.
No.
I don't have to drive.
People have cars.
Okay, what's left? That red and green shape is what?
Hey, Christmas.
No, it's Christmassy, sure, but what is it? All I can see is that what's true of the opposite side?
They look like trees.
You're congruent.
No, I can see that they're parallel.
The same.
Okay, so it's a parallelogram, isn't it? Okay, how about that? So we know always then that if we connect the midpoints of any random quadrilateral, the inscribed shape, and that's how we talk about it in math. If the shape is completely inside the quadrilateral, it's inscribed. That inscribed shape is a rectangle. A parallelogram. Always a parallelogram. To me, that's just interesting that it works out that way. You wouldn't expect it. It is, isn't it? Okay, so what if we want to prove a quadrilateral is a rhombus? You know, we talked about in general, there's a couple strategies we can take. We could use the properties of a rhombus. If we know, for example, that we've got a parallelogram with perpendicular diagonals, we know it's a rhombus. If we have a parallelogram with diagonals that bisect opposite angles, that's the other property we had of a rhombus, right? So we could use those, or generally easier, not always, but usually it's easier to just use the definition of a rhombus and show that it's just got four congruent sides. But either one would work. Now let's look at a specific example. What about this one? Say that we've got a quadrilateral drawn in the xy plane, so we know the coordinates of all four vertices. Okay, now what are my strategies here? How could I show that quadrilateral, what is that? KLMN is a rhombus. What could I do? Yes, sir. Okay, one thing I could do. Good. And I won't go through this, but we'll talk about how we could. We could find the slopes of all four sides. And what would we find? If I found the slope of KN and LM by just calculating rise over run, let's just do one of them, and we'll just, the rest of them we won't do now, but you can do later on your own. The slope of KN, that's just going to be 3 minus 5 over 6 minus 2. So what is that? 2/4? So 1/2? Everybody agree?
Yes.
So what would the slope of LM have to be then?
1/2.
It'd have to be 1/2, right? Because I would have to have a parallelogram with some conditions for this to be a rhombus, if we're using the properties. If I showed that opposite sides were parallel by calculating their slopes, then I got two possibilities. If it's a parallelogram, either I could show that the diagonals bisect the opposite angles. That might be hard to do. Or I could show that if the diagonals intersect at right angles, if they're perpendicular to each other, then it's a rhombus. Now let's just assume for the moment here that we've already showed that those sides are parallel, okay? Which we could do. This other job would really be pretty easy. Look at the diagonals that we create. If I look at LN, I want that to be red. LN, now what can you tell me about that line? If the y coordinates are both 3, what can you tell me for sure about that line? What's the slope going to be? 0, because what kind of line is it? How do we describe that kind of line? If it's flat, what is it? Kind of like if I look out on the horizon, that's probably pretty flat. Horizontal, sure. Okay, so we get a horizontal line, slope 0. Now, what if we look at the other diagonal, KM? Notice here that both of the x coordinates are 2. So if I calculate the slope of that, I'm going to get 1 minus 5 over 2 minus 2. I get 0 on the bottom. Can't do that. What's the slope? Undefined, sure. What kind of line is that? Vertical, right? So I know if this is a horizontal diagonal and that's vertical, sure enough, they have to meet at right angles. Because horizontal and vertical are perpendicular to each other, right? So that's one way I could do it. I could show that the opposite sides are parallel and the diagonals meet at a right angle. That would work. What's the other strategy? That would work. That's good. What else could we do? Just to go directly show it's a rhombus. What's the definition of a rhombus? Yeah, all 4 sides are congruent, so the distance formula would work. We could also just do this. Let's get rid of all that stuff. We could just calculate the distance from K to N, let's say, and from K to L, the lengths of all those sides with the distance formula, and what would have to be true of those distances? They have to be same, they have to be equal. Now, what do we do with those distances? Do we have to be fancy? Do we have to simplify them, make them decimals? No, not at all. We just have to get a number. We have to just show that the numbers are the same. So if I want to calculate the distance from K to N, let's say, well, that's just the square root of x2 minus x1 squared plus y2 minus y1 squared, right? Distance formula. So what's that give me? Let's see, x2 would be 6 minus 2, right? The difference in the x coordinates, squared, plus 3 minus 5. Okay, so let's see what we get. What is 6 minus 2? Squared? 16. What's 3 minus 5? Squared? Positive 4. So what is the distance then? Kn is just square root of 20. There's no reason for me to get all fancy and simplify that. I got an answer of the square root of 20. So if I get the square root of 20 right here, and the square root of 20 right there when I do the distance formula, and right there, then I know that this is a rhombus, right? Make sense? Okay, here's just a little summary of, whoops, maybe not. Well, anyway, on the PowerPoint, there's a little summary of what we just did there. Okay, last one, I think. Maybe not. This is an important one, though. This is maybe the most important of all of them, I think, because it's the weirdest. What type of quadrilateral is there? Okay, it looks like a trapezoid, doesn't it? In fact, what kind of trapezoid does it probably look like?
That looks like a rhombus.
A rhombus? What? No, I don't think so. All 4 sides congruent?
No, but it just looks like
Oh,
okay.
rhombus.
Really?
Yeah.
Okay.
Yeah.
Given the two options, I'm going to go ahead and go trapezoid on
Well,
this.
no, when I was little, there's like little things that look like that, and they were red. They told me it was rhombus.
Oh, they told you wrong.
Maybe that's why I'm in this math.
Oh, maybe.
It makes so much sense.
Okay, anyway, take a look at this now. So it looks like it's an isosceles trapezoid, but just because it looks like one means nothing. We have to be able to show that it's an isosceles trapezoid by using the properties of those things and the information that we're given to show that that fits the bill, right? It fits the characteristics. Well, before we can get to isosceles trapezoid, we got to get to trapezoid. What is the definition of a trapezoid again? You've already told me once. Okay, one pair, exactly one pair of opposite parallel sides, which means the other pair is not parallel. So I've got to show then, I've got to show here somehow that I've got a pair of opposite sides that are parallel. Now that goes back a ways. That's not even chapter 6 stuff. That's chapter 2 stuff, right? If I'm trying to show that two sides are parallel, that goes back to that two lines cut by a transversal stuff probably, right? So in this case, it looks like these are the two bases, doesn't it, of the two parallel sides of the trapezoid. So let's start with them. Okay, what if I extend those sides? Oh, get up there. So there are my two lines that we're trying to show are parallel. Now, if two lines are cut by a transversal, let's make one of these a transversal. How about this guy? Certain things have to happen for us to know that these lines are parallel. Now, what has to be true? If what, then the lines are parallel in this case. You know, this is that stuff where it could be like if alternate interior angles, but we don't.
Consecutive.
Okay, good. If consecutive interior angles are supplementary, then the lines are parallel. Well, they are. Look, 60 and 120 is 180, isn't it? So we know that these two lines are parallel, right? Make sense? Okay. Now, there's a couple ways we could do this. If this were, well, how could we show here? You tell me, I don't want to tell you. How could we show that the other two sides, AD and B, oh, darn it, that's not what I want to do at all. Right there.
Wow.
AD and BC are not parallel. How could I do that? Sure. I could assume they are and go back and prove they're not. That's one way. If they were parallel, that's great. No one suggested that all day. If they were parallel, then this would be a parallelogram, wouldn't it? Right? Does that make sense? If those two sides were parallel, this would have to be a parallelogram. And what's always true, say, of opposite angles in a parallelogram? If parallelogram, then opposite angles are congruent. Well, are they? No, those aren't congruent. So it's not a parallelogram, is it? No. So it must be a trapezoid. We know it has one pair of parallel sides, but it definitely doesn't have two, because then it would be a parallelogram. The other thing we could do, that would be just as easy, although I really like that way of doing it, we could take these two sides as being the lines that might be parallel, and let's take this line, say, as the transversal. Then that would mean that these two angles were consecutive interiors, right? But they're not supplementary. So those two lines aren't parallel. Either way we do it, though, we've got ourselves a trapezoid, don't we? Okay? Now, is this trapezoid, now that we've got our trapezoid, so let's just do this. We know we've got this going on. Is this an isosceles trapezoid? What are the characteristics, the properties of an isosceles trapezoid? If trapezoid, or if isosceles trapezoid, then what do we associate with that? Two congruent sides, right? Now, how could we don't know anything about the sides, but are there some angle relationships in an isosceles trapezoid? Base angles are congruent, aren't they? If trapezoid with congruent base angles, then isosceles trapezoid, right? So it's isosceles, isn't it? Okay? There's a lot of stuff going on there. That's a great problem. Ton of stuff going on. Okay, last one. What about this guy? The diagonals of quadrilateral ABCD intersect at point N to produce 4 congruent segments. AN, BN, CN, and DN. All those segments are congruent. Now, I've built something like that for us. There's a quadrilateral ABCD. We know that this is true, right? All those little segments, AN, BN, CN, and DN, are congruent. They may not look congruent in my picture, but who cares? The picture doesn't matter. It's the information on the picture that counts. And that says they're congruent, even if they don't look like it. So what kind of quadrilateral is this? Well, let's start general. Is it a parallelogram? Now, what has to be true of what is true of the diagonals of a parallelogram? What do? They bisect each other. Do these diagonals bisect each other? Well, here's the point of intersection, right? Is diagonal AC cut in half? Yeah. AN and CN are equal length, right? They're congruent. So yes, AC is bisected. What about BD? Well, sure. That segment and that segment are congruent. So it also has been cut in half, right? Even if it doesn't look like it. So it is a parallelogram. There's one thing we can say. Yes. Step 1. Parallelogram because diagonals bisect. So it is a parallelogram. Can we get more specific? Is it a rhombus?
No.
It might be, but what would have to be true of the diagonals for this to be a rhombus? They'd have to be perpendicular or bisect opposite angles. Now, we don't know. There's no way for us to know here that those diagonals are perpendicular. They might be, but they just as easily might not be. So it doesn't have to be a rhombus. What about a rectangle? What's true of the diagonals of a rectangle? True. What about the diagonals? Someone's already said it in here once this period. What about the diagonals of a rectangle? How are they related? They're congruent. Yeah. Well, let's look at these diagonals. Is the green diagonal, AC, congruent to the blue diagonal, BD? How come they? I heard yes. They are. How come? Okay, exactly. Let me paraphrase. That's exactly right. Because AC is built from the same 2 segments as BD, isn't it? All 4 of these segments are the same length. So if I put 2 of them together to form the green diagonal, and 2 of them together to form the blue diagonal, then those are congruent, aren't they? So because the diagonals, we know that it's a rectangle, because the diagonals are congruent. Okay, so it could be a rhombus, so it might end up being a rectangle and a rhombus. It could be a square, but it doesn't have to be. But it does have to be a rectangle, doesn't it? Does that make sense? You got to think about that stuff, I know. Yeah, the lecture's taped. I'll put it online. The PowerPoint is going online. You just need to go work on this stuff. So we'll be in the lab next 2 days.